My name is Steven, and today I'm going to be talking to you guys about how solar cells and solar panels work. First, I'm going to talk a little bit of history about solar panels. So in 1954, Gerald Pearson at Bell Labs invented the very first practical solar cell. This solar cell had a 6% power conversion efficiency, and it was silicon-based. In 1958, only 4 years later, the first spacecraft equipped with solar panels, Vanguard 1, was launched. Aboard this satellite, it had a silicon-based solar cell with about a 10% power conversion efficiency. Fast forward to today, and Solar City, which was founded in 2006, became a part of Tesla in 2016. And they produce commercial and residential solar panels, and that's shown on the bottom right. And these solar panels have roughly a 20% power conversion efficiency. So why is solar energy important? Solar energy is becoming more cost efficient with better power conversion percentages over time. Solar panels also can last decades, producing electricity the entire time, with no carbon emissions. Roughly 80% of global energy comes from the burning of carbon sources, and it's been shown carbon dioxide emissions are the leading cause in global warming. Today, only roughly 1% of global electricity production comes from solar energy. So how does solar energy work? And the answer to that simple question is semiconductors. So first I'm going to give you guys a few definitions that relate to the term semiconductor, and the first one of those being the conductor. So imagine you have a grandma on a trampoline, and above that trampoline are some monkey bars that grandma really wants to get to. Now in this case, the monkey bars are extremely low, so that grandma can be on the monkey bars and the trampoline at the same time. She reaches both at the same time. In this case, she can overlap both of those areas. Now this is analogous to a conductor, because in this case there is overlap between the valence band and the conduction band of a material. Now we're going to look at a similar scenario shown on the right. In this case, we have a small child sitting on a trampoline, and above him are the monkey bars. But this time, the monkey bars are extremely far away. This kid is completely defeated. He cannot reach those monkey bars, no matter what he does. In this case, it's analogous to an insulator. The little kid represents an electron, and that electron cannot travel between the valence band and the conduction band of the material, and that is what attributes the insulator's characteristic properties. So now we're going to look at the third case, being that of the semiconductor, and this is shown in the middle. In this case, you have a man representing the electron on the trampoline, which is the valence band, below the monkey bars, which is the conduction band. Now this guy is pretty tall. He's kind of close to the monkey bars, but he's not quite there as easily as the grandma on the left. Now he thinks, look at him, he's thinking really hard. He thinks that he can get to those monkey bars, but he just needs something that'll help him out, that'll bring him up to those monkey bars so he can do what he wants to do. He wants to have fun up there. So how do we do this? The very simple answer to this question is to introduce light into the system. Now on the left is when he was still on that trampoline, and he was questioning how he was going to get to those monkey bars so he could do what he wanted to do. And like I said, the answer to that is to introduce light. Now when you introduce light, look at him on the right. He's super strong, he's excited, he is ready to get to those monkey bars, and he is ready to produce an electrical current or have tons of fun up on the monkey bars. So now that we know how this guy is going to get up to those monkey bars, let's put this in a little bit more clearer terms in solar cells. So in solar cells, light produces enough energy for an electron or the person to jump from the valence band, or the trampoline, to the conduction band, or the monkey bars, in order to produce electricity. With the electron flowing in one direction, an electron hole is formed where the electron started its journey. Now looking at the diagram at the bottom, we see a similar diagram as shown before, but on the right, we now see this man super excited up on the monkey bars. He's now in the conduction band. He's ready to produce that electrical current. And you see his shadow down there? That's the electron hole. That's that positive charge that electron is going to leave behind in its absence. So how can we make this journey for this man to the monkey bars a little bit more easier? And this is about the efficiency of a solar cell. So in terms of a solar cell, that distance is called a band gap. And the way to decrease this band gap is to use different atoms or materials within the semiconductor itself. So shown on the left is the original state of the man. He's like close to the monkey bars, but he's not super close. He still needs to get there, right? But on the right, he's just a little bit closer, and that journey is going to be a lot easier for him. Now, in this case, you wouldn't need as much energy from the light in order to excite this man up to those monkey bars. So you wouldn't need as much light to excite electrons from the valence band up to that conduction band, where they would then produce an electrical current. Another way to make this man's journey up to those monkey bars is to make a bigger trampoline. If you've ever jumped on one of those really small trampolines, they kind of suck. But on a big trampoline, you can get pretty high in the air. In this case, that man could get to those monkey bars a lot easier. Now, in terms of a solar cell, if you decrease the electronic attraction to a nucleus by using elements with more populated orbitals, this decreases the magnetic pull between the nucleus and the electron, allowing the electron to excite more readily. Now, in this case, you would usually have larger atoms such as lead or tin, and these atoms have a lot of filled orbitals, so their electrons in the valence band are more readily excited up to the conduction band with the introduction of light. Another way that you can make this man get up to those monkey bars a lot easier is by changing what is beneath that valence band, or the trampoline. So on the left, imagine you have a trampoline in the sand, and you jump on that trampoline. That trampoline is going to dissipate a lot of energy into sand. It's going to kind of sink. You're still going to jump, but not as easily. On the right, with a nice solid surface beneath the trampoline, you are going to transfer most of that energy from the bounce into yourself, and you're going to get up to those monkey bars a lot easier. In the case of a solar cell, layering the solar cell with better materials is going to help that electron get from its valence band, and it's going to help it get excited up to that conduction band. Some of the materials that they use are a thing called spirometad and copper thiocyanate. Now, these materials help facilitate the transport of electrons and the electron holes throughout the semiconducting material and throughout the solar cell. So now we're going to take everything we've learned to this point, and we're going to help this man get up to those monkey bars as efficiently and safely as possible. So as we've talked about, changing the trampoline is going to help a lot. With a bigger trampoline, this man is going to be able to jump up to those monkey bars a lot better. And this is analogous to changing the materials within the semiconductor itself to something such as lead or tin. Now, these atoms are a lot larger and they have a lot more filled orbitals. And because of this, the electrons in the valence band are more readily excited, and they're able to leave the attractive pull of the nucleus of that atom, and they're able to go across into the conduction band and create an electrical current. So just by changing this atom or making a larger trampoline, we can help facilitate this man's jump up to those monkey bars. Now, another thing, it's a little hard to show here, but the monkey bars are down lower, closer to the man. And this represents the difference in band gaps. Now, because that monkey bar is lower, the band gap is smaller, so he does not even have to jump as high in the first place. Now, this is very important because if you have a limited amount of light hitting a solar panel, you have a limited amount of energy. And if you have a limited amount of energy, you want to get as many men very similar to him to be able to jump up to those monkey bars. So if one man doesn't have to have enough light, have as much light as prior, that man does not require as much energy, so that energy can be used somewhere else, and you can get as many dudes just like this guy up to those monkey bars and create a very strong electrical current. Also, like I had mentioned previously, is through the layering of the solar cell, we can help get this man up to those monkey bars. In this case, choosing the best materials such as a nice hard surface like concrete or asphalt underneath the trampoline. Most of the energy that's going to be produced through light and exciting these electrons is going to be used to excite those electrons, and it's going to make that excitation from the valence band up to the conduction band a lot easier. So overall, a larger trampoline or different atoms in the semiconductor, a smaller band gap, or being closer to the monkey bars, or having the trampoline on something that's going to help facilitate this man's jump up to the monkey bars, such as changing the layering in the solar cell, is ultimately going to help this man get up to those monkey bars shown on the right. And in this case, once he's up there, he's making that electrical current flow. The electron hole is back where he used to be, and that's shown through the shadow. And he is having a grand old time up on those monkey bars, and he is creating that electrical current throughout the conduction band. Now, I want to thank you guys for watching this video. I hope you learned something, a little bit how solar cells work, a little bit better. And me and this man, look at him. He's pretty excited. I want you guys to be excited about this man. And I want you guys to be excited about solar cells and clean energy. And I hope you have a great day. Thank you.